Welcome everyone. My name is Joe P. Thompson and I will be taking a seminar on the Stern-Gerlach experiment today. Let's step back for a moment before getting into the experimental analysis to remember the history behind this project. The Stern-Gerlach experiment was conceived by Otto Stern in 1921 and performed by him and Walter Gerlach in Frankfurt in 1922. Here we can see the pictures of the two eminent scientists who were behind this experiment, and Otto Stern obviously was a Nobel Prize winning scientist. He won the Nobel Prize in 1943 in physics. The main aim of the Stern-Gerlach experiment was to test the Bohr-Sommerfeld hypothesis that the direction of the angular momentum of a silver atom is quantized. Now, Bohr had originally used only one quantum number. Sommerfeld modified Bohr's theory to be known as the Bohr-Sommerfeld theory that describes atoms in terms of two quantum numbers. Here we can see the experimental setup of the Stern-Gerlach experiment and the apparatus that were used in this experiment. We can observe a hot furnace or oven giving out beams of neutral silver atoms. We can also see the non-uniform magnets that creates an inhomogeneous magnetic field here. Now let's analyze the procedure and the process that takes place here. Neutral silver atoms are emitted from the hot oven. The beam is then collimated by the two slits and passing through a non-homogeneous magnetic field. The beam is allowed to fall on a photographic plate. Now the question arises, why are silver atoms used to study spin of electron here? Let's analyze. Silver has an unpaired 5s electron. All other atoms are paired. And because they are paired, there is no or zero angular momentum for them. Now if atoms are paired, we know that theoretically, according to the Pauli's exclusion principle, only two spins are possible in one state, that is, spin up and spin down. Thus, there is no total angular momentum here. But here, silver has a 5s unpaired electron, and here S corresponds to L, that is, angular momentum equal to 0. But since last electron is unpaired, its spin gives a magnetic moment. And since the last unpaired electron has a spin and the orbital angular momentum is 0, we can solely study only the spin angular momentum here. Thus, silver is selected for this experiment. Since we discussed the silver atom, now let's discuss the role or effect of the magnetic field here. We can see a non-homogeneous field here. Suppose a uniform field is used, or the dipole will experience same torque. That is, if the beam moves through a homogeneous magnetic field, the force exerted on opposite ends of the dipole cancel each other out and the trajectory of the particles is unaffected. However, if the magnetic field is inhomogeneous, then the force on one end of the dipole will be slightly greater than the opposing force on the other end, so that there is a net force which deflects the particle's trajectory. If we just go back to the experimental setup diagram, we can see the irregularity and the non-uniformity of the magnets used here. This is the exact reason that there is a net force which deflects the particle's trajectory. Before we go into the experimental results, let's analyze the classical predictions that were expected from the experiment. If the particles were classical spinning objects, one would expect the distribution of their spin angular momentum vectors to be random and continuous. Each particle would be deflected by an amount proportional to its magnetic moment, producing some density distribution on the detector screen. If we go back to the experimental setup again, in the case of a uniform field, we can expect a thin line same as the slit. Here we can see the slit formed on the photographic screen as predicted by the classical prediction. Also, in the case of a non-uniform field, each dipole will experience a force according to their orientation, and hence the patterns are formed on the screen. Here we can observe the pattern formed on the photographic screen due to the inhomogeneous magnetic field. So we can say any orientation of this spin is possible according to the classical theory. Now let's examine the experimentally achieved results. The particles passing through the Stern-Gerlach apparatus were deflected either up or down by a specific amount. The initial beam split into two, corresponding to two opposite spins permitted by space quantization, and hence, as said earlier, only two orientation is possible, that is upstate and downstate, or plus half and minus half. So this confirms that only two spatial orientation is possible, that is up and down here. So in conclusion, the phenomenon of space quantization or electron spin, which were hard to visualize and imagine classically, are hereby demonstrated by Stern-Gerlach experiment, and this is the important significance of this experiment. Thank you.